Hey guys, so today we will be talking about protecting groups on sugar molecules. And why do we need protecting groups on sugar molecules? Well, let me show you.
If we wanted to make a glycosidic bond between two sugar molecules, which of these oxygens would react? Any of them could, making a big mess. To prevent that, we could protect all but one of these oxygens as shown in this molecule.
Here we show the protecting group as a simple P, but there are two types of protecting groups that we will learn about today. Here we see the acetate ester. This acts as a protecting group due to resonance of the lone pairs on the oxygen, stabilizing the molecule. This can be abbreviated as OAC. Here is a glucose molecule showing protecting groups on all carbons except for the anomeric carbon. Here we see the benzyl ether. This also can act as a protecting group. This can be abbreviated with OBN. This shows a glucose molecule with benzyl ethers protecting all carbons except for the anomeric carbon.
Alright, of these two protecting groups, the acetate ester gives you beta configuration at the anomeric center, and the benzene ether gives you alpha configuration at the anomeric center. Let's show you how that happens.
Here are our starting materials. As seen, all carbons are protected with the acetate ester except for the bromine. This bromine will attack the silver nitrate, creating a super leaving group. When this leaves, we are left with this intermediate.
In this intermediate, the lone pair of electrons on this oxygen will attack at this carbon, kicking the electrons up onto this oxygen here, giving us this key intermediate. We will now react this intermediate with an alcohol on a sugar group represented by R. We can see that this alcohol here is bonded beneath this carbon, blocking the alpha configuration. Therefore, when this alcohol attacks, it can only attack at the beta configuration, giving us this product here with the sugar at the beta configuration. This is called ankymeric assistance.
So due to this ankymeric assistance, we see that the acetate ester causes the beta configuration at the anomeric center. Now let's show you why the benzyl ether causes the alpha configuration. Okay, so we're back to this key intermediate. The bromine is left, leaving us with a positive charge on the oxygen. Here we see the benzyl ethers as protecting groups. If we react this molecule with an alcohol on another sugar, this lone pair can come in and attack here at the alpha position. This will then kick electrons here. This is favorable because when this oxygen attacks, this will be forming a CO sigma bond. The LUMO, the CO sigma star, will be stabilized by these lone pairs on this oxygen. They are in the same plane, giving us non-bonding to sigma star hyperconjugation. This leaves us with this product here, with the new sugar bonded alpha at the anomeric center. This hyperconjugation, stabilizing the molecule, is called the anomeric effect. Remember that. Alright, so that's everything. In conclusion, again with the acetate esters, we see the beta configuration due to ankymeric assistance.
And with the benzyl ethers, we get alpha configuration called the anomeric effect.
And that's it for protecting groups. Good luck studying, guys.